Hi, this is Arash and welcome to the epoxy channel. In this channel we're going to talk about the epoxy resins from the theoretical aspects to the most practical ones. So if this is the first video you're watching or if you're interested in epoxy resins, please like and subscribe to our channel for more videos. Today I'm going to present structural adhesives. To achieve an adhesive with the desired application characteristics, formulating is necessary, and therefore, currently numerous epoxy adhesive formulations are available. However, the majority of current commercially available epoxy adhesives have been formulated based on a surprisingly small number of ingredients. In case of the resin binder, various epoxy systems can be employed. They can range from a very simple primary aliphatic resins with low molecular weight to the more complex resins with higher functionalities or hybrid systems, for example, nylon epoxies, polysulfide epoxies, and epoxy phenolics. However, the most common epoxy systems employed in the epoxy adhesives is diglycidyl ether bisphenol A resins. Low molecular weight diglycidyl ether bisphenol A is often employed in liquid and paste adhesive grades, whereas for conditions where structural integrity is required, for example, in film adhesives, higher molecular weight variations of diglycidyl ether bisphenol A resins are often employed. The next important factor in the formulation of epoxy resins is the choice of the curing agents. Curing agents can be selected based on the nature of the base epoxy resins, application conditions, service temperature, required properties, etc. Although a large number of curing agents has been introduced, here again a limited number of curing agents are employed in epoxy adhesive formulations. The most common ones are amines, including aliphatic, primary and secondary polyamines, tertiary amines, polyamides, heterocyclic amines, and aromatic amines. Aliphatic amines and polyamides are often used in most commercial room temperature epoxy systems, which are to be discussed in the subsequent sections. In addition to the base epoxy binder and the curing agents, the incorporation of different fillers, extenders, and additives can result in some considerable improvement in the epoxy adhesive's behavior. The most important roles of the additives for epoxy adhesives include viscosity and flow properties amendments, shrinkage reduction, toughness enhancement, amending thermal expansion coefficients, modifying exothermic characteristics, and of course, cost reductions. Occasionally, pigmentation in the epoxy adhesive system is conducted separately in the binder and the curing agent, often in different colors. This allows the visual identification of a proper and homogeneous mixing. The most common hardeners for epoxy adhesive systems are amines, including aliphatic, primary and secondary polyamines, tertiary amines, polyamides, heterocyclic amines, and aromatic amines. Aliphatic amines and polyamides are often used in most commercial room temperature epoxy systems. The use of delta and theta in room temperature cure epoxy formulations is restricted due to the complexity of metering and as they may result in a rigid and possibly somewhat brittle cured adhesives. Polyamide and polysulfide curing agents impart flexibility and are preferred in epoxy adhesive system as they can distribute forces through the material matrix to reduce the stress concentrations. Anhydride and aromatic amines have also been employed, but to a limited degree. In hot cure adhesive formulations, they are often used. Advantages, disadvantages, and applications of different curing agents in epoxy systems have been presented in this table. Polyamides render low viscosity and their use is easy at room temperature. They show good bond strength and moderately high peel and impact strengths. However, they are comparably expensive and require long curing periods. They also have a high viscosity and their chemical resistance is not high. They can be used in general purpose adhesives or for encapsulation. Polysulfide and mercaptans show moisture resistance. They are fast cure and flexible. However, due to sulfur, they have bad odors. They also show poor tensile strength and their thermal resistance is also poor. They can be used in various civil and coating applications as well as for encapsulations. The next class is aliphatic amines. Their use is convenient and they are also fast cure. They exhibit low viscosities and are rather inexpensive. They show moderate chemical resistance. On the dark side, the metering is an issue here and they have a short pot lives. They have more health issues due to the higher vapor pressures. Their bonding is also rigid and show poor peel and impact properties. These curatives found in adhesives suitable for coatings, sealants, and encapsulations. These tables also provide information on other curatives such as amidoamines, aromatic amines, diC, and anhydrides. It should be mentioned that mechanical, chemical, and physical characteristics of the bulk adhesive material, degree of wetting, and adhesion between the adhesive and substrate, the employed substrate pretreatment method, and the design of the joint predominantly determine the properties of adhesive joints. Concerning the thermal stability and the high temperature limit of the cured adhesive, Tg of the system is predominant factor which is dependent on the type of epoxy resins, the employed curing agents, and the employed curing regime. Higher Tg values, for example 250 to 300 centigrades, can be obtained, while multifunctional epoxy resins and curing agents with hot cure temperatures regimes are employed in the formulations. However, common epoxy adhesive systems are formulated based on diglycidyl ether bisphenol A resins, diC curing agents, and a toughening agents, for example CNTB, and they show Tg values of around 100 centigrades. Structural adhesives are usually solvent-free formulation, but sometimes as sprayable solvent systems or water emulsions used to bond substances to produce high modulus, high strength, often permanent bonds. Epoxy structural adhesives are capable of transmitting structural stresses without loss of structural integrity and are often used for bonding concrete to concrete or other substrate in civil engineering. These types of adhesives can be used under moist conditions and are employed for bonding hardened concrete to either hardened concrete or wet concrete substrates. However, to provide a good bond in the concrete, the water level must be below 5 weight %. Epoxy structural adhesives are also used in steel reinforcement concretes, precast concrete objects, as well as anchoring steel bars in the concrete. Structural epoxy adhesives can be formulated to render various pot lives, making them suitable to be used in various conditions. Current commercially available epoxy structural adhesives are formulated as single component heat curing systems. However, multiple component adhesives that cure at either room or elevated temperatures are also available. Room temperature curing epoxy adhesives are often referred to as 2K components. K stands for a German volt component with K, indicating that the curing agents Part B and epoxy binders Part A are supplied separately and have to be mixed just before the applications. Upon mixing, the adhesive reactions starts immediately at room temperature or even at lower temperatures, result in a short working life. However, the complete cure and maximum strengths are achieved in much longer periods. In these formulations, very reactive curing agents are employed. Curing is again an exothermic reaction, and the amount of release heat is dependent on the formulation and the mass of adhesive that is mixed. Room temperature adhesives can reach their full strength in a short period, for example, few minutes or even several days, for example, 5 to 7 days. This period is determined by the type of the employed curing agent. However, most common room temperature curing systems are cured in 18 to 72 hours to reach full strengths. It is also possible to cure the room temperature curing epoxy adhesives at elevated temperature if faster curing is required. Polyamide or amidoamine curing agents are often used in these systems, and the base epoxy resins is a liquid diglycetyl ether bisphenol A resin. Other formulations may contain aliphatic amines, catalytic amines, amine adducts, or sulfur-based curing agents such as mercaptans. Two-part room temperature curing adhesives are generally preferred for large parts, as the energy consumption to heat the substrate for curing might be huge. One component room temperature cure epoxy adhesives, also called 1K adhesives, are also available, and for their curing, the energy source such as UV, light, or EB is required. Compared to 2K systems, one component epoxy often has a shorter shelf life, for example 3 to 6 months, whereas each part in a 2K component room temperature epoxy adhesives often has a shelf life of up to 6 or 12 months. Compared to 1K room temperature curing adhesives, the 2K systems of the same type exhibit greater flexibility, resulting in better low temperature performance, higher degree of peel and cleavage strength, and generally higher bond strength to flexible substrates. Finally, compared to elevated temperature curing adhesives, in room temperature curing adhesives, often a lower crosslink density or glass transition temperature can be achieved. Room temperature curing epoxy adhesives exhibit very long shelf lives, and as their name indicates, no heat is required for their curing. However, the curing process can be accelerated by applying heat. Less shrinkage and internal stress is rendered in these systems. They show moderate peel and bond strength, good toughness, and good heat and chemical resistance. They are comparably not costly, and their health issue is lower. However, during the application, they show short pot lives. This means that the adhesive have to be prepared and applied in small quantities, which makes their application tedious for the worker. Otherwise, the wastage is huge. In addition, their metering is also crucial. If higher temperature applied for their cure, mechanical and chemical resistance of these systems affected. Finally, their curing might be time-consuming. Fast curing epoxy adhesives are highly reactive 2K room temperature epoxy adhesives that reach their maximum strength in minutes at room temperature, and they are also capable of developing useful bond strength at temperatures as low as -20 centigrade. Accelerated aliphatic amines, Lewis acids such as BF3, and accelerated polymercaptan terminated curing agents are often used with fast curing epoxy adhesives. However, the use of polymercaptan and an accelerator as the main curing agent is more common in many fast curing epoxy adhesives. Polymercaptan-based fast curing adhesives are especially effective on alkaline surfaces such as concretes. In the commercial 5-minute epoxies, mercaptan terminated curing agents and amine catalyst accelerators are often used. Fast curing adhesives can be employed to bond difficult to clamp fixtures, for example, surface mounting electrical receptacles, brackets, and racks, or for rapid production line assemblies, for example, for bonding sections of reinforced plastics car bodies. They are also of great importance for applications where time matters, for example, for emergency repair of leaks or for bonding traffic buttons to highways when minimum traffic delay is essential. Fast curing epoxy adhesives are quite suitable for cold weather construction uses. Fast curing epoxy adhesives, however, suffer from a relatively higher shrinkage and brittleness, which yields lower peel and impact strengths compared to ordinary slower curing epoxy adhesives. Their curing yields higher exothermic temperatures, which may impose overheating risk and affects the final properties of the epoxy adhesive. In addition, due to their higher reactivities and short working time, they are more difficult to handle and apply, which results in higher wastage and variation in cross-linking density. Finally, due to their higher reactivities, these systems can impose higher health risks to the workers, for example, skin irritation problems. General-purpose adhesives are suitable for bonding various substrates used in construction, such as wood, stone, brick, metal, glass, rubber, plastic, ceramics, etc. These adhesives, often two-component solvent-free materials, show exceptional adhesive properties on cure and are suitable to fix damaged items which require a fine glue line. Curing agents for general purpose two-part room temperature curing epoxy adhesives include polyamides, amidoamides, and aliphatic amines. Polyamides and amidoamines confer flexibility and a degree of toughness to the cured epoxy, whereas the more reactive aliphatic amines provide moderate temperature performance but good chemical resistance. Properties of curing agents used in general-purpose epoxy adhesive have been presented here. Based on the data which have been presented here, suitable curing agent can be used in the formulation for a certain application. Heat curing epoxy systems can be either 1K or 2K. Liquid or paste forms are more common in heat curing systems. However, there are also solid adhesive forms, for example powders and films, available. As their name implies, these systems are designed to be cured only at elevated temperatures, for example a minimum temperature of around 80 centigrades. These systems still have a finite working life at room temperature, which is much longer than that of room temperature curing epoxy adhesives. Similarly, the catalyst or curing agents has been incorporated directly with the epoxy resins in the 1K elevated temperature curing epoxy adhesives, and no metering and mixing is required. However, these systems exhibit a limited shelf life and might need special storage conditions. Compared to room temperature curing systems, elevated temperature curing epoxy adhesives, also called heat curing epoxy systems, provide better shear strength, especially at elevated temperatures. They also exhibit better environmental resistance. However, they usually provide poor toughness and peel strength due to their rigidity. They possess greater internal stresses than in room temperature curing epoxy adhesives. They exhibit higher shrinkage upon polymerization. They are also more brittle than the room temperature curing adhesives, and they render the heat hazard as the heat has to be applied. The viscosity could also be problematic as the heat has to be applied, and the reduced viscosities might yield joints with not enough adhesives available for bonding. Elevated temperature curing epoxy adhesives are often given a post-cure. Actually, in the curing process, the system is first cured to a state in which the bond is capable of handling, where the fixturing used to hold the parts are released, and the bond component goes to the next manufacturing stage. After reaching the handling strength, the joint is post-cured by applying heat until it achieves full strength. Moreover, many epoxy adhesives are beta-stage resins, in which, during the cure, resin experiences a semi-cured stage, in which the reaction between the epoxy binder and the curative agent has taken place but has not been completed. In this semi-cured stage, the adhesive is still fusible and soluble and to some extent flowable. However, upon applying further heat, the curing procedure is completed and the bond formed and stiffened. Beta stage enables to formulate resins for one-component adhesives, for example films, powders, and preforms. Therefore, it yields a better consistency amid the metering and mixing stages for the user and reduce the risk of wastage. Aromatic polyamines and solid forms of diglycidyl ether bisphenol A epoxy resins can be used to produce beta stage resins. Thanks for your attention. I hope you enjoyed the video. Please share your thoughts, questions, or comments, and I will come back to you soon.
Thank you.